If I know the straight chain, I'm going to draw my ring. So carbon 1 is over on the far right side. So this is going to be carbon number 1. Carbon number 2, 3, 4, 5, and 6 makes like an upside down question mark. So carbon 1 comes down to carbon 2, across to carbon 3. Carbon 4 should look like it's like on the opposite side of carbon 1. Okay, so carbon 1's always in the far right corner. Carbon 4 should be on the far left corner. Then it comes up to carbon 5. And then remember, carbon 6 is not chiral because it has 2 hydrogens. So it really doesn't matter. You just write it as CH2OH. Okay, so that's the one that's like sticking up. So see it here? So it's like sticking up off of carbon number 5. So it sticks up in that ring. So this is 1, 2, 3, 4, 5, and that's 6. And then oxygen spans 1 and 5. Okay? So oxygen spans 1 and 5. So that's how you end up with the hexagon with the little oxygen in the sort of like upper right corner. That oxygen actually was carbon number 5's oxygen. So it was this one is the one that now is part of that ring. So remember, in determining where the alcohol or hydrogen groups are in carbon 2, 3, and 4, all of the groups that are on the right side of the straight chain all point down. So that means that this is carbon number 2, carbon number 3, carbon number 4, carbon number 5. So on carbon number 2, I know there's an OH. On carbon number 3, I know it's an H pointing down. On carbon number 4, with galactose, there's an H pointing down. So OH, H, and H tells me which ones point down in the ring structure. And then the ones that are over on the left side of the straight chain, those will be the ones that point up. So that means that carbon number 2 has a hydrogen pointing up. Carbon number 3 has an alcohol group pointing up, and carbon number 4 has an alcohol group pointing up. So it's just the ones down the left side versus the right. So I'm not going to ask you to draw them, but recognizing this, so if you have a straight chain and you have a ring, you should be able to pick them out. Just remember that in the middle carbons, carbon 2, 3, and 4, in the straight chain, everything on the right will end up pointing down as a ring. Everything on the left ends up pointing up as a ring. Carbon number 5 has this hydrogen. That's the only thing it's got. It doesn't have an alcohol attached because its alcohol became part of the ring. So then the last thing to figure out if it's an alpha, that tells you, or beta, that tells you where to put your alcohol group on carbon number 1. So since we have one that is the beta, I want my alcohol group to point up. So remember that that's the beta conformation, and that means the hydrogen would point down. So there's an alcohol and a hydrogen on carbon 1, 2, 3, 4 going around, and their positions are really determined based on the structure of that in the positions on the straight chain. So really what I want you to be able to do is just recognize. So looking at a ring, you should recognize the straight chain and vice versa.
Would we ever have to recognize
but you don't have to recognize like, oh, so it'll always be like the aldohexose. So it'll be where you have an aldehyde and you have a 6-carbon chain. Versus like the 5, because the 5 looks different. And if you have a keto, it actually looks different. Like fructose ends up having like a little pentagon shape instead of the hexagon shape. But just worry with these ones. These are the more common ones. So like, for example, with this, if you look at fructose, do you see how that looks different? See how fructose forms like a little 5-membered ring? So remember, that's fruit sugar because it's a ketone. So that's why. So its carbon that had a double bond was carbon number 2, not carbon number 1. So notice it's still, though, this was the one that was the double bond. It's always over on the right side. Okay, so it's always like the right corner of the sugar as a ring is the one that used to be the double bond oxygen. So then we went on and we talked about, okay, well, how do these things get put together into disaccharides? And that leads into the polysaccharides. So we talked about how you name these. Condensation reactions always pull a hydrogen off of one molecule, an alcohol group off of the other, and that forms the link, which is called a glycosidic bond. So just remember, glycosidic bonds are the bonds between sugars. And in fact, we can name a glycosidic bond based on which carbons are connected. So that's the numbers. The 1 arrow to 4 means carbon 1 and carbon 4 are connected. But we also use the alpha or beta because that tells you where the alcohol group was on carbon 1 or carbon 2. So in this one, remember this carbon 1 used to be the double bond oxygen, right? So in these molecules, carbon 1 is the double bond oxygen. So that's the one that you're looking at that becomes alpha or beta when you look at the ring structure. So looking at this one's a beta because it's sticking up. And so when it forms a glycosidic bond, that means that the bond is always going to angle upward. If this was on this, where this hydrogen is, that would be in the alpha position. So it would always be pointing down when it forms a link. So if you look at the shape of an alpha 1 to 4 glycosidic bond, do you notice that it always looks like this? I always say it looks like a V. Alpha 1 to 4 will always have a V shape. Beta always ends up looking like this. So it always ends up looking kind of diagonal because of the angle that the alcohol group was when it was connected. So you have alpha 1 to 4 is the V-shaped glycosidic bond. Beta 1 to 4 ends up having more of a diagonal. I will tell you, some books like to try and they'd want to put the two sugars side by side instead of having that funny diagonal. And so it'll look like this. So it'll look like this. So it looks like a zigzag, but do you see how that's like going up compared to it going down? So this one, maybe I've got it drawn. Hold on, I think I might have it drawn backwards. I think it goes this way. So you end up with these two lines, and it goes like this. Yeah. So that's like the same position because the bond goes up onto this side and then ends up coming down to the other side. So because of it's a beta, the line would go up. And the only reason they do this is because that would allow you to put two sugars side by side. So I'll give you an example. I'll show you. So this is maltose. Maltose is an alpha 1 to 4. So notice alpha 1 to 4. It looks like the regular little V shape. Then we have the next one. Come on. So the next one, we have lactose. So lactose is a beta 1 to 4. So notice the angle goes up. So it's kind of an easy way to remember. Beta is always going to have kind of a diagonal arrangement. Alpha is always going to be more of a V if the two sugars are side by side. And then the last one we did sucrose. And sucrose is kind of strange because in sucrose, the two carbons that are connected used to be the double bond oxygens. So the top one is glucose, the bottom one is fructose. They are linked where they used to be double bond oxygens as a straight chain. And so because of that, you actually end up naming the position of the angle of the bond on the glucose and the angle of the bond on the fructose. So see how this one is going down. That is why this is called alpha. But this one is going up, which is why they call it beta. So that is why this one is called an alpha beta 1 to 2. And that's the only one that ends up, those two sugars kind of look like they're stacked. So then we talked about the sweetness scales. But there's the example. So there's the one. And I did finally go back and draw it the right way. So this first one. You should be able to look at these and tell me what kind of glycosidic bond is this. So the trick is, so remember that look at the left sugar. Okay, because the left sugar is always going to be where your carbon 1 is. So look at the left sugar. If the angle coming off to the oxygen is up, that's what? Up is beta. If it's coming down, you know then it's alpha. Then figure out which carbons are being connected. So you just number them. So in this first one, look at the left sugar. Is that alpha or beta? It's alpha. Right? So I know that this is alpha, and it's connecting carbons what? 1, because the left sugar, this is carbon 1, 2, 3, 4, 5, 6. So if I was numbering, remember you'd number like upside down question mark. But then I got to number the one that's down below. Where do I start my 1? In that same spot. So this is carbon 1, 2, 3, 4, 5, 6. So this is alpha 1, 2, 6. Does that make sense? So I'm connecting carbon 1 of the left sugar to carbon 6 of the right sugar. So look at the one that's like up and to the right. So in that one, look at the left sugar. Which way does it angle? Well, it comes up. Do you see that? This is the example I showed you where I said it looks like a zigzag. So this, do you see how this puts them side by side? Okay. But when you look at the angle of the bond, you can see it's at a diagonal. So if you see the diagonal, okay, so this one, because that left sugar, the angle goes up, this is what? Beta. And it's connecting carbons what? 1 and 4. So it's connecting like the right carbon on the left sugar and the left carbon on the right sugar. So it's like connecting them. They look like they're side by side. So a book will put it like that just to be able to, instead of having them like this, it takes up less room on a page. What about the bottom one? Alpha what? One and 4. It's just a different way of drawing alpha. So instead of a V, this one looks kind of like a U. And again, it just is just different ways that different drawing systems use. So if you see that, don't let that throw you. So this and this, same thing. Okay, like a V shape or a U shape with that oxygen. So these are the same. And then also this and this, same thing. It's just different ways of drawing the same glycosidic bond. Does that make sense? Okay. All right. So you tell me this one. Okay, first you got to pick which one has, that's not an alpha beta, which one of these is the oxygen connected to carbon 1? The top one or the bottom one? The bottom one, right? So remember this is carbon 1. So this is the one that you want to start your numbering. Okay, because that's the one that used to be the double bond oxygen, not the one above. So it's the one below that used to be the double bond oxygen. So that means that what was its shape? Was it alpha or beta? Pointing up is beta. So this is beta connecting carbon 1 and carbon what? 2. So you see that's alpha and beta connecting carbon 1 and carbon 2. Or sorry, not alpha beta, but just beta. Then this bottom one. Bottom one is beta, right? Because it's going up. Connecting 1 and 4. Because they're still side by side. So now this one that has 6 sugars. So this leads us into the polysaccharides, because this is what you're going to see. It's not just 2 sugars. Now there's actually 6 sugars. So some of the sugars, like this one, what's this? Alpha what? 1 to 4, right? Because they're just attached side by side, and they've got a U, the V shape. So those are alpha 1 to 4. But then what's this one? Same thing. This one? Same thing. Do you see that even this one is the same thing? That all of those are alpha 1 to 4. That just creates these glucoses that are like side by side in this long chain. Very common in starch. But then how's this one different? It's a no. So again, in that one, you've got to find where's carbon 1. Where's carbon 1? Is it on the top one or the bottom one? See that this is the top one, so that's carbon 1. So that's the one that you want to look at to see if it's pointing up or down. And so that one is pointing which way? Down, so it is alpha, and it's connecting carbon 1 and 1, 2, 3, 4, 5. This one's 6, right? So see it going around the upside down question mark? So this would be an alpha 1 to 6. So they call that a branching bond, because you'll have this long chain of alpha 1 to 4, and then you'll have an alpha 1 to 6 that creates a branch.
So if that is still alpha and one beta.
Because this is carbon 1, right? So the one up here, that's carbon 2. So find carbon 1, and that determines if it's alpha or beta. So if you have 2 linked together, one of them is going to be the one that used to be the double bond oxygen. So find carbon 1. So it doesn't matter if one's above the other or vice versa. Find carbon 1 in the example, and then determine if it goes down, that was alpha. If it goes up, then that's beta. Okay? And then figure out what it's attached to on the other sugar. Because that one, it's attached to carbon 2. Carbon 2 is not the double bond oxygen, right? So carbon 2 was just an alcohol group that ended up being connected. And then the one over there, carbon 1 is the upper, so the one that I'm talking about here, carbon 1 is the one above, because that's carbon 1. And then going down, it connects to carbon 6. So carbon 1 is going to be what they call the anomeric carbon. It's just the carbon that used to be the double bond oxygen. That's the one, when it closes, that's what determines if it's alpha or beta. Okay?
And was that called finding the glycidic bond?
Naming or identifying the glycosidic bond. So any bond in a sugar is a glycosidic bond. But you can name which carbons are connected based on the position that the alcohol had on the 2 sugars when they joined. So then this leads us into the last group. So now we've got the polysaccharides. So poly means many. So when we talked about mono and disaccharides, we said they're 1 sugar, 2 sugar. These, we're talking about hundreds to even thousands of glucose units. So poly is many. So I'm going to split these into 2 groups. We're going to talk about the digestible polysaccharides. And then we'll talk about the undigestible polysaccharides. So digestible polysaccharides means that you can break these molecules down. So starch is the first one. So starch is found in granules of plant cells. So they are in all of your grains, rice, corn, potatoes. So that includes things like all of your breads, pasta. They are all going to contains different types of starch. So wheat makes a starch, oats make starch, barley makes starch, rice, potatoes. So really, starch is a mixture. So starch is kind of a general term. It's a mixture of two polysaccharides. The first one is called amylose. So amylose is about 20% of starch. Only about 20% of starch is made of amylose. And it's anywhere from 250 to 4,000 glucose molecules. So it is a chain all connected in a long continuous chain of alpha 1 to 4. So alpha 1 to 4, does it look like a V or a zigzag? So alpha, if I drew a little glucose molecule looking like that, right, just not putting in all of the parts, a V is the link. So these are connected. That would be 2. Then I'd have to do another one. A little hexagon with the oxygen in the upper right corner. That's 3. I'd have to do 250 to 4,000 of those. Every single one connected by an alpha 1 to 4 linkage. So huge in comparison to like glucose. Comparison to sucrose. These are really large molecules. Amylopectin is kind of like amylose, but it has a branching system. So amylopectin is really about 80% of starch. So it starts off as a chain of alpha 1 to 4, but then it has branches about every 25 glucoses. So if I had, and I'd have to draw 25 glucoses, which is a lot, I'll just draw glucose as a circle to try and make it look simpler. See, each one of these is a glucose. If I have 25 glucoses all linked by alpha 1 to 4 bonds, when I get past that 25th, I'll have a branch. And that branch has alpha 1 to 4, but the branch is in alpha 1 to 6. So that's this branch, and now I can have a long chain. Do you see how this can kind of almost look like a tree? Okay, it's kind of like ends up being this chain with these branches, and if the branches are long, then the branches can have branches. So you can end up with this sort of like intricate shape. This molecule that can have this branch and then this branch, and then you can have branches and branches coming off of here. So this molecule gets pretty big. Size-wise, this is again, can be in the thousands of glucose units. So it makes this really large branched structure. But you make an enzyme called amylase. And amylase breaks alpha 1 to 4 bonds. So we digest it. So we can break alpha 1 to 4, and we can break alpha 1 to 6. So we make enzymes that can break this down. So that means if you eat a molecule of amylose, it'll take a while, but all of those sugars can be broken down into single sugar units. So we make an enzyme to be able to digest this. So that's why if you eat grains, potatoes, rice, pasta, bread, you ingest it, it gets broken down, and you can absorb all the glucose out of that molecule. So here's sort of like the alpha 1 to 4. So amylose, pretty big. It actually tends to make a coil. So see the chain they did in like yellow? They did one in like just a long chain, just to show you that they would be glucose, linked to glucose, linked to glucose. All those would be alpha 1 to 4. But when you have these, because of this shape, they tend to form a chain, which is kind of an interesting looking coil that they form. So when you eat anything that's this, if you eat any kind of starch or amylose, enzymes in your saliva actually start this digestion. So these enzymes begin to break up the chain. So you break it, and you break it, and you break it. And first it just randomly gets broken along the chain. So it gets broken from a really big sugar into smaller and smaller pieces of many sugars. And then those begin to get broken down, and those get broken down. And eventually it will get all the way down to where you have individual glucoses. And that is when they get absorbed. So you'll have breakdown occur, more breakdown occur, and eventually you'll have monosaccharides. And when you get to the monosaccharide stage, then you can absorb it. So it has to get broken down all the way down to single little circles, single little glucose units. You can't absorb anything bigger. It won't go through the lining in the GI tract. So you have amylase in your saliva. You even have amylase secreted as part of your pancreatic juice. Those help to break the links between the sugars. This is going to take a while. So this is why when you eat a starchy food, it typically takes 3 to 4 hours before you begin to see a change in blood sugar. Because remember, this is sugar. It's still glucose. So once you absorb it, it does affect your blood sugar, but it doesn't affect it quickly like the simple sugars. When you eat simple sugars, you see a change that can happen like in minutes. You can start to see a change in blood sugar. So here, it's a much slower, steady increase. But if you were looking at blood sugar over time, it would increase it. Now, if you have a functioning pancreas, what gets kicked in? What gets secreted if your pancreas works? Your blood sugar goes over 110 and your pancreas makes insulin. And that helps keep it from going too high, right? But if you don't have insulin, even eating starches, your blood sugar can end up going above what it needs to be. So simple sugars are not the only thing that a diabetic has to look at. Simple sugars can change it really fast, but complex carbohydrates can still cause it to get into the range of that hyperglycemia. So monitoring both kinds of carbohydrates, not just sweets. You've also got to watch the breads, the cereals, the pasta, the potatoes, because those also can have a dramatic effect on blood sugar over a period of time. So when looking at amylopectin, so I kind of like this picture. So this is the majority of starch. It's amylopectin. And so see how it kind of looks like this big branched thing? So lots of alpha 1 to 4, but also every 25 glucoses, you have an alpha 1 to 6. So you end up with a branch off of the chain, and then those get big and you have branches. So again, remember, this can be thousands of glucoses. We digest these too. We can break alpha 1 to 4. We can break alpha 1 to 6. But in doing so, it means we're absorbing glucose. So those are the starches. So diabetics need to monitor starch as well as sugar. Because both of those can have an effect on blood sugar. Starches are just a little slower, but they can still raise your blood sugar. So here's the other one. So there's another digestible sugar, or polysaccharide, sorry, it's not a sugar. Another digestible polysaccharide, it's called glycogen. So glycogen, though, is not found in plants. Glycogen is found in animals. So starch is in plants, right? It's in the seeds of things, it's in grains. So all of our examples of starches you saw, those are all plants. This is how animals produce a polysaccharide. So animals take sugar and store it for in between meal times. So animals can store blood sugar as glycogen. Most glycogen is stored in your liver and skeletal muscles. It looks almost identical to amylopectin, so that's branched. So it's branched, except it's a little more branched. It's about twice as branched as amylopectin is. But when we looked at this one back here, you can kind of think glycogen looks a lot like this. Glycogen looks a lot like this branched chain of glucose. It's just actually more branched. Glycogen production, since we're animals, we make glycogen. So we under the influence of insulin, so when you eat, remember I told you, so you eat something with a carbohydrate, you break it down, you absorb that glucose, your glucose goes up. Insulin secretes from the pancreas, which starts to bring your blood sugar down. As it comes down, one other thing that your insulin does is it tells your liver and skeletal muscles, take excess glucose out of the blood and store it as glycogen. I always think of glycogen as your in-between meal sugar source. So it's a way for you to store sugar for the times that you're not eating. So when are you not eating? Every 4 hours. When you're sleeping. So glycogen is kind of like your blood sugar regulation method for while you're asleep. So if you're not eating, then over time, your blood sugar starts to come down. Well, remember I said if your blood sugar goes below 60, then you start getting shaky. You might start feeling kind of dizzy. You start it's difficult to concentrate. Hypoglycemia is an issue, just like hyperglycemia. So glycogen is there for when your blood sugar starts to go below 60. Then this can get broken down. And when it gets broken down, it releases glucose into the blood. So it helps to keep your blood sugar from dropping too low in between any type of eating. So it helps to maintain a constant glucose when sugars are not being consumed. And I always think of when you're asleep. Because most people sleep for 6 to 7 hours. And so during that time, your blood sugar would actually drop too low because you're still doing metabolism. Your cells are still needing sugar. So a lot of people that are athletes, if they have a game or they have a marathon or they have some kind of activity where they're going to need a lot of energy the next day, they will usually eat a higher carbohydrate meal the night before to try and maximize the amount of glycogen they have. So that way, if they're out running, they don't have time to eat because they're exercising for 3-4 hours in a game or in some kind of competition. They may burn a lot of their blood sugar. So their blood sugar, instead of going down, it can actually access glucose from glycogen. So I just think of it as kind of a storage form or a way that animals can kind of maintain blood sugar during times that they're not eating. So here's a picture that kind of shows the three of them. So these are starch. So these are your flour, grain, pasta, bread, cereal, all of those things. That's your starch is composed of these two. Amylose is just a chain. Amylopectin does have some branching. We digest that no problem. Glycogen is what we actually make as a way of storing blood sugar. But it looks a lot like amylopectin. It's just actually more branched than amylopectin is. So those are digestible. These we can break them. We can break glycogen down. We can make glycogen because we're animals. Starch, we can break it down. We can't make it because we're not plants. But we can digest it. We can break it down and use it for energy. So now, what about fiber? So this is the non-digestible polysaccharide. So it's not digestible. So you remember that the bonds for starch and for glycogen are alpha 1 to 4 and alpha 1 to 6. We can make those bonds. We can break those bonds. Cellulose is beta 1 to 4. So let me blow this up just a little bit, see if my new updated computer, oh well, doesn't do it. But if you look at this, it's such a challenge to look at and not be able to, we should have just blown this one picture up. Nope, Oh, I don't know how to make it. It won't. It just won't. It used to hold that. Like I used to be able to zoom and it would stay, but now it won't stay. So in this one though, what I want you to look at is looking at this type of bond. So a beta 1 to 4, the glucoses that they show, when you look at this bond, can you see that it looks like the bond goes up, which is, this is beta. So the bond here goes up, but the glucose that's next to it, they flip it upside down. So that makes it look like an upside down V, but it's actually not. It's actually angled correctly, but I just flipped the second glucose down. The third glucose is turned straight. So that's why it ends up having this, it creates this totally straight line that allows chains of glucose to line up and create like fibers. So that one picture, that green picture, is like an electron microscope picture of cellulose, which is like cotton or bark from a tree. And so you can actually see these strands in it. Those strands are that tight packing of the chains of glucose, and that helps to create this super strong structure. The whole reason you can have a tree 60 feet tall is because of cellulose. So the fibers of cellulose strengthen the wood and form a really rigid structure. We don't make this, right? We don't make cellulose or fiber. So we're much more flexible and bendy than plants are. Cellulose is built around cell structures. It's part of their cell wall, and it's part of the bark on trees. So it helps to create this really sort of tough, fibrous material. And the other big kicker is we don't make the enzyme to break a beta 1 to 4 bond. So remember, we can break alphas, but we don't make the enzyme to break a beta 1 to 4 bond. So that means that when you eat this, like you're like, I don't eat tree bark and I don't eat cotton. Well, you actually do. If you eat any bran flakes, you do. Because that's kind of like what there's a large amount of fiber in things like that. So there is 2 kinds of fiber. So there is fiber that is called soluble, and it's because the fibers are not as tightly packed. So this, when it gets heated, will kind of loosen, and so it forms more of a gel. So I always think about oatmeal. So have you ever had oatmeal? Everybody here has had oatmeal, yes. You know how oatmeal has almost like a gravy kind of taste to it? Like it's got like this sort of gel kind of material. I mean, I like oatmeal. Oatmeal's fine, but you have to kind of think like the texture of it. It's got this kind of gel-like taste to it. That's soluble fiber. So when you boil the oats, the fiber in the oats softens and thickens and creates that. It helps to make you stay full because it soaks up water, so it actually swells in your stomach. It helps you feel full, and they have shown that it actually helps to slow sugar and cholesterol absorption. So if you're going to eat some bacon, have some oatmeal with it. So it helps to slow the absorption of sugar and cholesterol, and it can help you feel full. So that's a benefit, especially for people that are like trying to maintain and regulate blood sugar. Oats. Oatmeal beans. So I don't know, like if you've had refried beans, you know, like the texture of them. So they're kind of thick, the refried beans. Apples, like if you ever had like baked apples, you know how apples they'll get that kind of gel-like taste to them. Even carrots, when carrots are cooked, they'll get sort of soft, mushy, but they'll get like this kind of gel taste to them. All that soluble fiber. But the thing to remember, there's no calories in fiber because you don't digest it. So what happens? It doesn't get digested. It doesn't get absorbed. It passes through you. The other kind of insoluble fiber, though, insoluble fiber is where those strands of glucose are tightly packed. They don't absorb water. Most insoluble fiber are the covers on grains. So if you think about like corn, if you think about like brown rice, the potato, like if you get a potato from the store, it can sit like in the vegetable bin for like months. Sometimes it seems like at least a month. It can just sit there. It doesn't dry out. Why? because it has a cover on it. The peel on the potato is insoluble fiber. So it really creates almost like this waterproof cover on vegetables and fruit. Apples, oranges, all have this insoluble fiber. It protects the fruit, it protects the seed. But if we eat it, it doesn't absorb water and it doesn't get digested. So it has much more of a laxative effect. So it actually helps to add bulk to the food that's in your large intestine. Things like whole grains, seeds, brown rice, cabbage. Cabbage has a lot of insoluble fiber in it. All of the skins on your fruits and vegetables. Those are all things you can think of as being an insoluble fiber. They don't get digested. It doesn't like soften. It really just like moves through you. The reason that this is helpful or important, increasing or adding fiber to your diet helps to reduce your risk of colon cancer. So your colon is your large intestine. So the large intestine, it's basically the last 4 feet of your gastrointestinal tract, your GI tract, or your digestive tract, the last 4 feet. The job of the large intestine is to just absorb water, collect unabsorbed material into solid form, and then move it out. And so for most people on a daily basis, your colon, the large intestine, goes through this series of contractions so that it actually pushes unabsorbed material into a more solid form. It absorbs water out of that solid material and it moves it along. So you get like this kind of like contractile motion that occurs. And for most people, it actually occurs on a pretty regular basis. And that even for some people, it's like same time every day. Like you poop every day. So you have like this sort of like cycle that occurs. Most of the time it coordinates with your diet. When you eat, then it's much more common. I think of it, your large intestine is trying to move things out to make room for what's coming in because you've eaten. So you need to actually move stuff along. Unabsorbed material that doesn't have very much fiber will stay in the large intestine. So then you got to think about, okay, well, what's not absorbed? Unabsorbed material. You absorb carbohydrates, you absorb fats, right? And oils. You absorb water, you absorb salts, you absorb proteins once they get digested. We haven't talked about them yet, but you do absorb those. So what's left? What's left in your food? If you take out carbohydrates, salts, water, proteins, fats, oils, what's left? Preservatives, artificial flavors, artificial sweeteners, artificial colors. All of these things, they're not nutrients. We don't absorb them. So these things, if you don't have any fiber in your diet, these things stay in your large intestine. So they're artificial. And so some of them have been found that they can cause irritation to the wall of the large intestine if they stay there for a prolonged period of time. So how does your large intestine respond to this irritation? It may form a polyp. So a polyp is just where you have a growth. It looks almost like a mole. You get a growth on the surface of the large intestine. Some of those polyps can actually grow pretty big. So your large intestine is roughly about 1.5 inches in diameter. So the opening of the hole is about like this. So if you get a polyp that's now like this, what's that going to do to the tube? So if your polyp looks like this, so here's your tube and stuff has to go through and now you got this polyp that's this big. Yeah, it can create a blockage. Okay, so it can affect how well things do move through. That means this stuff hangs out even more. That growth can sometimes become abnormal and grow faster than it should. And then sometimes it can metastasize and then spread to other parts. So this is where your large intestine is very vascular. There's a lot of blood supplied to this tube. And so if it spreads, then it can go to other organs. So that's the big concern, which is why they say adding fiber to your diet helps to keep you regular and it helps to move things out of the large intestine that you don't need. You don't need that because it wasn't absorbed. So obviously it's something that wasn't useful to the body. And so that's like the benefit of it. And I will tell you that when I moved here, so I've been here since 95, but in the first couple of years of living here, I was like really, really surprised at like some of the diets of some of my students, because I would ask, like I would say, like, you know, that everybody should poop every day. And I have had students come up to me that say like, I like poop like once a week. And I'm like, what? What do you mean? Then the discussion, well, why? Like, so then the question is, so do you eat vegetables? No, I don't like vegetables. Do you eat salad? No, I don't like salads. All right, then. So we start going through and I'm like, you have no fiber in your diet, right? So I have like, yeah, I like fried chicken. Okay, well, that's grease and that's bread that you digest and that's protein. All of those things, there's absolutely no fiber in it at all, okay? If they eat vegetables, they eat vegetables that have been cooked till they're mushy, okay? And if you cook that, you can actually break down some of the insoluble fiber. So that becomes this like discussion. I had a girl came in, like in her family, diverticulosis occurred and colon cancer. And she was like, I didn't even know any of this. Like, why is this? And she was like, didn't have a regular bowel movement. Like once, twice a week was normal for her. So like had this whole discussion. She doesn't like brown bread. No, I don't like brown bread. I like white bread. Okay. White bread has much lower fiber. So that fiber, the cover on the wheat grain has been pulled off. So all that's left is starch. So this discussion then led to, well, try to add this. What about that? Would you eat this? So like we had this whole discussion. I finally was like, there's a cereal called toasted oatmeal squares and they taste pretty good and they don't taste like you're eating like wood bark. And so she was like, all right. So she started adding she just added like a cup of that to her daily diet. She like worked up. And at the end of the semester, she said, no, I poop like 3 times a week now. I've never done that ever before in my life. I didn't think I thought that was completely normal. And I was like, if you have a family history of colon cancer, diverticulosis, which is where you get like little pockets in the large intestine, if you have that, you really want to try and make sure that you get fiber regularly in your diet, just to make sure that like basically everything's getting pushed through as time goes on. All right, now it's back. Okay, so those are just showing sort of the 3 different kinds. So we've got amylose and amylopectin from plants, but those are always like the grain. It's the inside of the vegetable. That's where you're going to find your starches, the inside of the seeds, the potatoes, inside of the rice. Cellulose is always the outside cover. So if that's like hysterical. So my significant other, he is like if he eats the sweet potato, he eats the potato and he like throws away the peel. And I'm like, that's like the best part. And he was like, no, it tastes like dirt. Like he doesn't like potato skins. And I'm like, that's where all the fiber is. You should like throw the inside out and just eat the outside. But like my dogs are hysterical. That is their favorite part. The skin on a potato, like a sweet potato, like you roll it up and they act like you're giving them candy. It's because there's a little bit of sweet potato, which is really sweet tasting to them. So they eat the peel too. But that's the difference between. So when you think of amylose and amylopectin, always think of that starchy interior to the vegetable or grain. Cellulose is always the outside cover. So you can get more fiber by eating like the outside of the apple, not peeling your apple, actually eating the cover on the apple, eating vegetables that are really crunchy. The whole reason they're crunchy is because of cellulose. When you cook vegetables till they're mushy, then a lot of that soluble fiber dissolves and it's in the water that you boiled it in. Most people don't drink that. Most people like pour that off and then serve the vegetables with some more butter on it. Okay, so that's just sort of like the normal Southern diet is really like not too much coleslaw is about the only thing, like at Parker's that you're like, okay, so there's some fiber in the coleslaw and that's all. Pretty much nothing else. Because even their potatoes are already peeled. Their potatoes come completely peeled. So I'm like, so there's a lot of starch and carbohydrates and fats in there. But I'm like, there's not very much in terms of fibrous. So you have to eat like twice as much coleslaw. You're going to get any of the mix. All right, last topic in this chapter. So last topic in this chapter is about blood types. So maybe So if you take an A and P, maybe you know what your blood type is. Does everybody know what their blood type is? No? No? Okay. I really just need to start doing this in lab because I'm not sure that they do this anymore anywhere else. But, so blood type is, you've probably heard, like, maybe you know if you're A, you're B, you're AB, or you're O. Okay? So we're really not talking about the positive and negative. Like, I'm O positive. But we're just talking about like what the letter designation means. So the ABO markers are actually talking about carbohydrates that are on the surface of your red blood cells. So they're sugar groups on the surface. So here are 4 of the possible sugar groups, and you don't have to remember what their structures are or even their names. But there's galactose. You've heard that before. There's a couple of odd ones. One's called fucose. Notice that it's carbon 6 is odd. Carbon 6 doesn't have an alcohol group on it. There's N-acetyl galactosamine, which has like a strange nitrogen group and it's like an amide on the end there. And then the one N-acetyl glucosamine is kind of like a glucose with a little amide on there as well. So those ones are like these 4 sugars. So if you are type A, well, I'll give you type O first. So if you're type O, so this is me. If you're type O, your red blood cell has a set of 3 sugars attached to its surface. So that means I've got like a whole bunch. So I've got 3 sugars, 3 sugars. And I don't mean like you only have one of these. Like the surface of my red blood cell has these 3 sugars on it. So lots of them on the red blood cell. This is your RBC. Okay, so you got lots of groups of 3. So the 3 is that N-acetyl glucosamine. It's kind of like a lilac, a light purple. Then you have galactose, which is orange, and then you have fucose, which is yellow. So we have this kind of like light purple, orange, yellow pattern. My immune system knows that pattern. So my immune system cells, my white blood cells, which are floating around with my red blood cells, my white blood cells bounce up against red blood cells all the time. And they're always feeling other cells because they're always looking for things that don't belong. So I'm type O, so my white blood cells bounce up against these 3 sugars and they're like, yep, that's normal. Bounce up against another one, that's normal. And they just move all around, constantly feeling. But if you're type A, you have what I have. So do you see that type A has the same 3, the light purple, orange, and yellow, but they have an extra. So if you look at their red blood cells, the surface on their red blood cells, they got a blood cell, they got the same 3, but now they got an extra. So they actually have the normal pattern of 3, just like O, but they got this extra one. It's the light yellow one, okay? So that pattern, does it match mine? No. So if I, as a type O person, if I get type A blood, my immune system cells, my white blood cells, bounce up against this carbohydrate pattern, and it's like, no. This is not supposed to be here. And this will actually trigger an immune response. My white blood cells will attack and destroy type A blood cells because I'm type O. So if it's not the same, if it has anything different, then it's going to be rejected. And that's the reason why when they give somebody a transfusion, they want to type their blood. If you're type B, you don't match A and you don't match O. If you're type B, do you notice they have the same basic 3 carbohydrates on their red blood cells that all of them have, like O has, but they actually have an extra galactose. So that extra galactose is, again, would make it look different to me. So I'm type O. I cannot get type A because that 4th sugar is weird. I cannot get type B because that 2nd galactose would be trigger an immune response. So type O, I can't get A blood, I cannot get B blood because they have a sugar that doesn't exist on mine. So what do you think type AB people are? Well, what do you think their red blood cells look like? So if they're AB, type AB actually has two different kinds of sugar groups. They have a group just like A and a group just like B. So their red blood cells will have the ones that look just like A, the set of 4 that looks just like A, and it'll have the set of 4 that looks just like B. So type AB has both groups of sugars on their red blood cells. So if I'm type O, can I get that? No. So that would be completely foreign to me. So no A, no B, no AB for type O people. But what can I get? I can only get O. Okay, so being type O, you can only get O because I have kind of like the simplest pattern. So no fancy patterns for me. It's got to be just the simplest pattern. But, so what about type A? Can they get type B? No. So they cannot get type B because you see it's not the same. So it would look different. What about AB? Could they get type AB? So if I'm A, if I got AB, that means I'd get some B. So I'd get some sugar combinations like B. So that would be foreign as well. So I cannot get B or AB if I'm type A. I can't get anything with a B, basically. What if you're type B? You can't get anything with what? A. So B cannot be transfused with type A or AB because it's got that weird N-acetyl galactosamine, the light yellow one. That wouldn't match. What if you're type AB? What can you get? So type AB has the pattern of A and the pattern of B. And A, B, AB, and O. So they can get anything. Nothing is foreign to the type AB. So I think of them as being like, they're the universal receiver. You can give any blood to AB because they have the pattern of A, they have the pattern of B. Now think about the pattern of O. Do all the blood types have the pattern of O? They all have, do you see they all have the 3? So if I give O to A, it'll have the same pattern of 3. A has an extra one, but their white blood cells will still see the basic 3. That is why O can be given to anybody. It is sort of the simplest pattern. And so it's a pattern found in all blood types. And that's why they call O what? They're the universal donor. And if you go give blood and they type your blood and you are type O, they will call you incessantly. I know. So I finally, I had surgery and I was like, I don't think I should be giving blood after surgery and anesthesia. And I'm still trying to get through all this. So she was like, all right, well, I'll just put you off for 12 weeks. We'll call you. And so they have already. They've started back. Because I had it in the end of November. So December, January, February. Now here we are, beginning of March. And I've already gotten a couple phone calls this week. So, I go and give blood regularly. It doesn't bother me. I don't have any problems with it. But I'm O positive. And so that means that they can give my blood to type A, type B, type O, type AB. As long as it's positive, they can give it to it. So it's in pretty high demand and need. And so I think with COVID and stuff, people kind of stopped giving blood. So their resources have really been decreased. So it's a much bigger issue. But that's really where it comes from. So O has the basic, think of type O, it has the basic pattern of 3 that all blood types have. That's why you can give O to anybody and it won't reject. AB has all the possible patterns. So you can give blood to any blood to AB and they're good. They won't go through any kind of rejection. You have roughly, say 6 pints, 6 liters of blood that's in your body completely. About 1.5 gallons. That's about as much. The more rare is AB. AB is the most rare. B is the next. A is then like next to the most common. O is the most common. O and AB. And it does depend on populations too. So different populations, type A may be more prevalent than type O. But it just depends on like your heritage. Like if you're European versus being African versus like my mother's Native American, everybody in my family is type O. It's like extremely common amongst Native Americans, type O. Like this, you just don't ever see people are in AB. Like, what? They're just not. So, and it is genetically determined between parents, but so my father's O, my mother's O, so we're all O, everybody in our family. So just remember, O has the basic pattern of carbohydrates, and that's why it can be given to anybody. It's the universal donor. AB has all the patterns, so they can get anybody's blood. They're the universal receiver. If you give blood, type A to type B, so if you give blood to a patient that does not match that blood type, then rejection will cause destruction of those red blood cells. So I said, you have your body, an adult human, has about somewhere between 5 and 6 liters. So we'll say like 1.5 gallons of blood. If they transfuse more than 20% of your blood, so if you get really much more than a pint, if you get more, which is basically like a unit. So, if you go give blood, they like collect it in a little bag. So it's a certain amount. They call it a unit. So a unit really is very close to a pint. So if you transfuse a person with more than 10 to 20% of their blood volume and it's the wrong type, then this can cause blood cell destruction, which can then lead to liver failure and kidney failure because the destroyed blood cells end up clogging your filtering organs. So your liver and kidneys filter out stuff, so they can end up being damaged because of it. So that's why it's really important. That's because they don't want to take your blood. You don't have enough. You already don't have enough. And so that's a really common issue for females, and that's because you menstruate. So you lose blood every month that guys don't do. So it oftentimes, like when I was younger, not so much now, but when I was younger, it really would depend on what time of the month. If it was just before my period, I could go donate blood. But if it was just after, I might come back looking anemic. Like they'd actually say, oh, your blood's not, they have to measure the density of your blood to make sure there's enough red blood cells so that you would be okay to donate. So some people, especially little girls, like little stature girls, can oftentimes be like borderline anemic, and so they might not let them donate blood. Just depends on how much red blood cells you have. So mismatch of blood can actually be life-threatening. So there is like a chart that shows, and this chart's actually correct. So notice that all the blood types can get O. AB can get anything. But AB can only give to AB. So I'm telling you, if you're type AB, the Red Cross is like, yeah, okay, thanks. Because you can't give their blood to anybody but AB. Right? So all of those are limited. The only one that AB can give blood only to AB. But O can be given to anybody. So this is that universal donor, all types. And O and A are the most common. So if you're type A, then your blood is pretty useful because that means that you can donate. If you're type A, then you can donate to A, which is real common. You can donate to AB. But O is by far and large. I can attest to that. I really do have to call them back and make the appointment.